now. Great. And here we go. Hello, everyone. This is the 13th edition of the LightOn AI Meetup. My name is Jacopo Poli, and I'm the lead of machine learning at LightOn. We are a startup in Paris that develops hardware for large-scale machine learning computations. And it's been some time now that we organize these meetups to share interesting ideas in the community. And for this edition, we have Beidi Chen, who is a postdoc researcher at Stanford, and she is going to talk about SLIDE and MONGOOSE LSH frameworks for efficient neural network training. So I'm going to stop sharing my screen, and you can start your presentation, Beidi. Thank you again for accepting the invite.
Thanks. I will start the presentation now. Can you see my screen? The full screen of the slides? Okay, great. Hi everyone, I'm Beidi. I'm presenting our recent two joint work, SLIDE and MONGOOSE. Those are LSH-based frameworks for efficient neural network training. Those are in collaboration with great researchers from Stanford, Rice, Intel, Columbia, Princeton. I'll be mainly talking about MONGOOSE since it's the most recent one, but we'll also cover the details about SLIDE in the middle, because that's what MONGOOSE is built upon. Currently, with the exponential growing data and model size, neural network training needs more computational resources. Since we have limited resources in practice, it is necessary to overcome the bottlenecks and perform efficient training. First, for school or small business, it would be lack of machines or budget. It will be concerning. And for industry, even with unlimited resources, time is everything. So especially for some online services or frequent training. So let's take a look at the scale of the models. It's just explode these days. And the bottleneck we're focusing on today is the computation for giant matrix multiplication in linear layers preceding a softmax. For example, attention layer in transformer models or the output layer for extreme classification models. We know that approximate matrix multiplication can trade off accuracy and efficiency. So several existing work, including SLIDE, we built, and Reformer take advantage of this trade-off and showed in some special cases how to use locality sensitive hashing to do approximate matrix multiplications in MLP and transformer model training. However, it is not that widely used because LSH itself will introduce new overhead when doing the approximation, which can lead to bad accuracy efficiency trade-off. For example, naively applying LSH may cause 20 times slowdown or 10-point accuracy drop compared to the brute force matrix multiplication in neural network training. So in this talk, we'll be mainly show how you can improve efficiency accuracy trade-off for LSH to achieve up to 20 times speed up and 4 times reduction in memory while maintaining the same accuracy. Before going to the details, let's walk through the outline. First, I'm going to talk about some background of LSH and data-dependent hashing, which will help better understand the problem setting and our proposals. Then I will introduce a key observation that the neural network weights and their hash code change slowly. After that, I will show how we can take advantage of the observation and design our framework MONGOOSE. Finally, I will show how MONGOOSE achieve better accuracy efficiency trade-off in multiple real-world applications. LSH is a randomized hashing algorithm, which has the property that If two vectors, x and y, are similar to each other, the probability that they share the same hash code or be hashed to the same bucket and a hash table is high, and vice versa. Here are simple illustrations of how to use LSH in neural network search. In the figure, we have 5 data points and 1 query colored based on similarities. Given a query, the goal of neural network search is to find data points that are within some distance threshold to the query. And with LSH, you can perform approximate neural network search in sublinear time by space partitions. Specifically, there's a pre-processing phase where we partition the space with hash code. In this example, we can see 1 hash table and k hash functions producing binary hash code. So the space is partitioned into 2 to the k regions corresponding to buckets in the table. Then we store IDs of these data points into different buckets based on their k hash code. We then have the query stage, where we want to find the neighbors of this query. We extract the candidate neighbors based on the k hash code of the query and search over the candidates. LSH makes the search space smaller and more efficient by filtering a set of candidates. Let's take a popular example hash function called sign random projection. Let there be 2 points, x and y, shown in the figures. Then consider a random hyperplane passing through the region. So if x and y lie on the different side of the hyperplane, like the space of h1, they will have different hash code. 1, 0, the other one's 1. Otherwise, if they lie on the same side of the plane, like in the case of h2, they will have the same hash code. And the probability of the hash code being the same corresponds to the angle of x and y, which is monotonic to the cosine similarity. Then how does LSH, a neural network search algorithm, realize approximate matrix multiplication in neural network? Let's take a vector matrix multiplication as a toy example. The first step is neural network search we just talked about. Here, the query is the input x in this linear layer, and the data is the weights w in this layer. Here we assume the weights have been preprocessed in the hash tables. Then right before the application, we're going to query the neighbors of x among weight columns. In this case, we have 2 and 5. They're similar ones, and they're likely to produce high inner product. Then we only do the multiplication with column 2 and 5, and others will be set to 0. Now, in our case, since we have a softmax nonlinearity after the matrix multiplication, and softmax is dominated by the large entries, you can approximate it just by looking at the large entries correspond to the high dot product between x and columns of w. However, LSH brings 2 kinds of overhead. The first one is the query overhead. Recall LSH hash functions randomly partition the space independent of the data. In practice, to guarantee the accurate neural network search, we need to maintain many hash tables, each with multiple hash functions. So in the query phase, we have large overhead due to querying multiple hash tables. And this is further exacerbated due to bad data distribution that can cause several heavily populated buckets that require longer query time. Query overhead issue of LSH has been well addressed by recent works in data-dependent hashing, which can partition the data more efficiently. A natural question is, can we just directly use this data-dependent hashing in neural network training? And the answer is no. because of the update overhead. Recall the toy example where we use neural network search to do approximate matrix multiplication in neural network training. Unlike the traditional neural network search setting, during the training, the weights are gonna change over time, and LSH will need to update its hash tables accordingly. So if we fail to do that, in some examples, we see large accuracy drop due to the inaccurate neighbors. For example, if weight 5 has been updated and become pink, it should be updated to bucket 1-1. And the cost of maintaining LSH hash tables is already very expensive in neural network training setting. Although data-dependent hashing can reduce the query overhead, you will make the update more expensive. The goal of the work of MONGOOSE is to address these challenges we just talked about. First, while there are a lot of work on how to use LSH in neural network search where the data are fixed, this lack of understanding in neural network training setting where the model parameters are changing. Second, the high query overhead of LSH results poor accuracy efficiency trade-off for approximate matrix multiplications in neural network. And lastly, the evolving parameters introduce high update cost. And to overcome these challenges, our first goal is to have a better understanding of model parameter update dynamics. Then we'll show how to take advantage of the understanding and reduce the update and query overhead. To this end, we're introducing MONGOOSE, a learnable LSH framework which realizes these three goals. The assumption was to use LSH, we have to update the hash table whenever weights are changing. The good news is when studying the weight training dynamics in neural network, we observe a very important phenomenon. The weights are slowly changing. This is an example side-by-side comparison of weight changes and their hash code changes for each epoch. Hash code are on the right. We see that there are large change in the first 1 to 2 epochs, and then there's a plateau. And on average, you only need to perform LSH update for 1 to 5% of the weights in a wide range of cases. This is the main insight which MONGOOSE was built upon and improved over slide. We show the detailed benefits we can get from the previous observation, followed by related issues on how to take advantage of them. First, if we have an oracle tells us when to update and when not to update LSH, we would reduce the frequency of LSH update by 100 times. And with such low update frequency, it gives us an opportunity to use data-dependent hash functions, which would reduce the query overhead, as we explained earlier. However, in practice, we do not have this oracle. And even we have this low update frequency, it's not obvious we can have this realize the shorter query time using data-dependent hash functions without compromising on the update time. Therefore, in the next part, I'll first recap what original slide algorithm is, and then I'll show you 2 key components of MONGOOSE. One is an algorithm for scheduling LSH updates, and the other one is how to learn parameterized LSH hash functions at low cost. Now we take a look into a workflow of a toy example, efficient adaptive sampling with slide. First, we build a bunch of hash tables for the weight vectors, neurons in each layer separately. Note that we only seek the IDs of the neuron, not the weight vectors. So in the example, for hidden layer 1, we compute the hash code using H1, and a neuron 1 will go to the first bucket, and 2 and 4 to the second, and 3 goes to the third one. And for a given input, we first compute the hash code of it with the corresponding hash function H1 in hidden layer 1, and then use the hash code to find a set of active neurons stored in a corresponding bucket. In this case, the hash code is 2, and neuron 2 and 4 are activated for hidden layer 1. And then the output of the hidden layer 1 is to use as the query for sampling active neurons for hidden layer 2. And sampling is guaranteed to pick the large activations with high probability, and forward and backward passes only do the computation on active neurons. So the cause is at the same order of active neuron set size. And similarly, using the output of hidden layer 1 as the query to H2, we get active neurons 3, and the second hidden layer. Please note that even for the same batch, each input will activate its own set of neurons in each layer. So weight changes need to be updated, and we simply update the hash table in each iteration.
Did it freeze only for me?
It or not, we're just describing the process. So on this diagram, the curve stimulates the weight or the hash code changes along the training. And the red dot lines, the arrow pointed to, represent the iterations that the scheduler triggers LSH update. Otherwise, there will be no update. For example, this is how LSH partition the current iterations of the weights. Same color represents they have the same hash code or are neighbors. Let's say this weight 5 has been updated. Then if the scheduler decides there's no update, the hash code for 5 will remain the same. And if the scheduler decides there is update, the hash code will correspond to the new weight. And then we also provide the guarantees for our scheduler, condition, and weights changing slowly, and advantages in support for massive parallelism on modern computation architectures. We can theoretically show that our scheduler is always faster than the naive sequential updating strategy while not hurting the accuracy. Next, we introduce our second component in MONGOOSE, Learnable LSH. The goal of learning the hash functions is to better partition the data and to achieve lower query time. Let's take a closer look on how we realize the low-cost learning. We use parameterized hash functions like simhash or cross-polygon LSH, and the learning process involves collecting the positive and negative pairs from the previous iteration. The positive pairs come from the ones that are supposed to be the neighbors, like 1 and 2 in our example, and the negative ones come from the ones that are not neighbors, but are partitioned together by hash functions like 4 and 5 in our case. Then we perform supervised learning to update the hash functions. Let's put things together here. This is the MONGOOSE complete workflow. From time T1 to T2, at each step, our scheduler decides to perform LSH update or not. If there is update, we first update the hash functions and then the hash tables. In summary, based on the slowly changing weights observation, we design MONGOOSE, which has the smart scheduler and low-cost learnable LSH algorithm. And the next step is to show how does MONGOOSE do in practice. The first task is extreme classification on the Wiki 325K dataset, where there are 325K classes, and the base model is the wide MLP layers. We see from the result table that Mongoose get 20 times speed up and 4 times memory reduction while maintaining the same or even better precision in one compared to the naive MLP model. And compared to Flight, which is vanilla LSH, we use 2 times less memory and 14 times less time speed up while achieving more than 7 point better accuracy. And take a look at our paper for more data sets in this category. The other task is language modeling using a transformer model. The baseline is Reformer, which uses vanilla LSH to approximate the attention layers. Here we can see on both copy and in Wiki 8 dataset, Mongoose achieve 0.5 lower loss and lower perplexity using approximately the same resources. And this is an ablation study on why currently we use LSH over other data-dependent data structures like graph-based ones, HNSW. And the first 3 columns benchmark the reconstruction or updated time of HNSW and Mongoose, and, with LSH. And it seems like LSH scalability is much better and is also much better in real applications. In summary, we present a key observation that hashcode of model parameters change slowly, which provides the space for a data-dependent LSH framework. Then based on this insight, we could design a smart scheduler to update LSH according to the parameter changes. And also we managed to learn to adjust LSH hash functions based on current parameters at low cost. Based on above, our framework Mongoose achieve better accuracy, efficiency, and trade-off of LSH than prior works like Flight for efficient neural network training. And there are several interesting future directions we'd like to explore more. One is we can design more efficient data structures for neural network search and neural network training. The second one is other neural network models, or can we design new ones that can exploit LSH or neural network search and approximate large matrix multiplication? And thanks. That's the main part of the talk, and welcome to ask questions and discussions.
Thank you, Beidi, for the presentation. It was really interesting. So now it's the time for the questions that you might have. You can either ask them yourself or write them on the chat, and I will ask them for you. So are there any questions? I can ask the first one, so maybe you're shy. I was wondering, how does this method interacts with like half precision training or like reduced precision in neural networks weights? Like, I don't know if that has an effect on the way you do, like the way LSH works.
Yeah. So the question is how is the accuracy and efficiency trade-off that LSH or data-dependent hashing has in neural network training? Is that the question?
And it's more like a lot of these models, like transformer models, for example, it's really common to train them with like mixed precision, where you have some weights that are in float 16 instead of float 32.
Oh, I see, the mixed precision.
Yeah, and I was wondering if you've tried to use a slide and mongoose with this kind of technique, like together? And if you did, like, how do they interact? Because I imagine that might have an effect on LSH.
Yeah, so we tried on the mixed resolution training, and I think that way of reducing the memory and saving the time is a perpendicular direction as how LSH help with the training. So these two factors can add to work together to have a even better reduction. Yes.
Okay. Thank you for the answer. I see there is a question in the chat. Is there any hope to accelerate the convolutional part of neural networks instead of the fully convolutional last layer by
Sure.
MONGOOSE?
Yeah, that's a very good question. So the best regime that LSH can speed up the matrix location is the very wide or large matrix locations. And also, as you see, like in observations, we're saving the weights in hash tables, and we're assuming that the weights are not changing that frequently or small changes. So those are the two kind of assumptions that LSH will have lower overhead and work well. But in the convolution case, since the bottlenecks is not about the size of the weight, it's kind of like the size of the input. So that since the input change for each batch and each training data, and even the weights or the filters are not going to change frequently, or they're going to have minor changes, maintaining them in the hash table won't have too much speed up currently based on like the naive way of applying that. But we are definitely working towards the direction that we can somehow group the inputs, which is the computational bottleneck, so that we can perform similar speed up on the convolution. Yeah, that's the current process.
Thank you for the answer. And there is another question by Daniel. In the slide about the results for extreme classification, I noticed the MLP with MONGOOSE achieved a higher accuracy than the baseline MLP model. And is this because MONGOOSE is acting as a regularization method?
Yes, that's what we believe is true, because we consistently see and different data sets is performing slightly better even than the plain MLP model. And since MONGOOSE is performing the sparse activations and updates, we think is because of the regularization. Yes.
Thank you. Are there other questions? Yes, a new one. Can you explain in more detail how the detection of the necessity to update the LSH works?
Can you repeat the question?
Yes, if you can explain in more detail how you detect when you need to update the LSH.
Oh.
Like, how does that work?
Sure. So this is a slide for how we do the scheduling. If you see the diagram on the left, this is like the key observation we're based on. So the intuition is we're gonna update the LSH hash tables more frequently at the beginning of the training, and then and less frequently in the end. So that's like the general intuition. And how we detect that in this iteration, are we gonna update it or not, is by maintaining more efficient than a copy of the weights. So we're gonna detect the change at low cost. So if the change is over some threshold, by that lower cost data structure, we're deciding this iteration, we're performing an update, otherwise we won't. And because that lower cost data structure is very cheap to compute, so you can do that more frequently.
Great, thank you for the answer. And there is a very practical question in the chat that is the code for this method available somewhere to use it?
Yeah, so this paper, the MONGOOSE paper is gonna be appeared in iClear, and before the conference, we're gonna release the code. And we already had the link in the paper, and the full code will be appear there. Yes.
Nice. Okay, another question. What kind of hardware did you use to get these performance results?
What other?
Yes, I guess what CPU, GPU, these kind of things did you use to
For
get the
MONGOOSE
results?
or, okay. For MONGOOSE is actually GPU based because we're able to show the results. So for different tasks, we're going to use the different code base. For example, the extreme classification task, this is built upon slide. And we're doing the hash tables and the memory more intensive things on CPU. And then computing the hash code, this kind of matrix multiplication things on GPU. So it's a mixed use of CPU and GPU. For the language modeling task, this is based on a transformer model. And since Preformer is built fully on GPU, and then MONGOOSE is also fully performed on GPU.
Thanks. Any other question?
I don't quite understand where you get the memory savings from, right? Because you need to also save multiple hash tables. So how do you get a reduction in memory? I would assume you get an increase in memory consumption, but it's very good if you don't, right?
Yeah. So for the memory saving, that's more on saving the memory for matrix multiplication. Remember, we're working on really large matrices. So if you're gonna make multiply with like a smaller matrices, that's gonna save the memory. So for the hash tables, since in MONGOOSE we're able to reduce the number of hash tables, plus each hash table will only take to the order of the number of neurons. We're saving the IDs, not the exact weight in a hash table. So that's not gonna take too much memory. So that's why we have the savings. So the overhead is not dominating the savings we have for large matrix multiplication.
Okay, thanks.
Thank you.
Any other question? I have a very simple and practical one. What is the largest, widest model you've trained with this method?
Yeah. Are you talking about the parameter size or the size of the matrix multiplication?
Guess both. I don't know.
Sure. Yeah, because like the concept is a little bit different for the MLP layer and attention layer, because the attention layer is not about the number of parameters, it's about the number of tokens in the input, because it's doing like an n square kind of computation. So for language modeling, the maximum size we're doing is over 10,000. And then for the extreme classification, for the weight, like the parameter dimensions, I think in the paper we say it's like 670K. So this is an example of 325K. And those are the scales of the extreme classification data sets.
Okay, thank you. Are there other questions? I don't see anyone raising their hand. So I guess we can finish the meetup here. And I want to thank you again for the presentation. And Yeah, it was really interesting. We are gonna post the video on YouTube and a short blog post on our blog, I think tomorrow. So yeah, I will send you the link and information. And yeah, people are clapping on Zoom. So if you want to clap in real life, you can unmute yourself too. And thank you very much again.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you, Beidi.
Thanks.
Thank you.